This is part 2 of the lectures covering the seasons. In part 1 of the lecture, I went through how the seasons work as seen from space. That is, if you can get off the Earth and just simply watch what happens as the Earth orbits the sun. Understanding the seasons from that perspective is rather straightforward. The seasons are caused by the fact that the Earth's equatorial plane is on an angle with respect to the ecliptic, the plane of the Earth's orbit about the sun, by about 23.5 degrees. And then towards the end of part 1 of the lecture, I then constructed the following celestial sphere diagram, going from the picture of how the seasons are viewed from space to the seasons now being viewed from the ground. From the ground, the seasons work in the following way. First of all, starting on June 21st, the summer solstice in the northern hemisphere. This is when the sun reaches its northernmost extent, north of the celestial equator, projected onto the sky here. And then as the Earth rotates day by day, the diurnal circle associated with the sun is not quite parallel to the celestial equator. Instead, the following happens. At noon on June 22nd, for example, the sun will be here. At noon on June 23rd, the sun will be here, and so on and so on. By the way, as I continue here, once again, I'm making the following assumption. If you are, say, standing on this line of longitude of the Earth, it is by definition noon at your location. So then therefore the sun would be on the meridian as seen from that location. And then continuing from June 21st forwards on the autumnal equinox, going from north to south, this is then when the sun crosses the celestial equator. It then reaches its southernmost extent south of the celestial equator on the outer solstice, December 21st. And then after that, the sun reverses. So for example, on December 22nd at noon, the sun would be here. Noon on December 23rd, the sun would be here, and so on. It eventually crosses the celestial equator once again on the vernal equinox, going from south to north. That's on March 21st. And then the sun continues northwards from there, back up to June 21st, once again, completing an entire year. So if you could watch the sun day by day, say at noon, starting on June 21st, and then all the way back to June 21st, once again, you would see the sun ultimately do this like so in the sky. It would appear to trace out a line in the sky. That's actually, however, not quite the case. The reason for that is because as the Earth's orbiting the sun, it doesn't do so at a constant speed in a perfect circle. It orbits the sun in an ellipse. Because of this, the shape that is traced out in the sky as you watch the sun over the course of the entire year is not a line. Instead, the shape is referred to as the analemma. The analemma is shaped like so. And here's what this shape represents. Let's say, for example, that you could look at the position of the sun in the sky at noon on June 21st. This portion of the celestial sphere diagram. That's up here. And then let's say that you could look at the position of the sun in the sky at noon on December 21st. That's here on the celestial sphere diagram. That's down here. But as the Earth's orbiting the sun in an elliptical manner, it also very slightly changes its speed as it does. It turns out that when the Earth is closest to the sun, that actually happens in early January, it's moving fastest in its orbit. When it's furthest from the sun, that occurs actually in early July, it's moving more slowly in its orbit. So this slightly changing orbital speed of the Earth and the fact that the Earth's orbit about the sun is not a perfect circle ultimately gives rise to this shape. Now, I described this shape, the analemma, in a little bit more detail in a screencast that accompanies this lecture. Go ahead and pause this lecture here and then go ahead and access that screencast now. Okay, now you've seen that screencast and the detailed explanation of the analemma, let's move on from there. Okay, what I'm going to do is I'm going to use this diagram here, this celestial sphere diagram, in order to understand what the seasons look like from any vantage point on the Earth. Similar to what I did in the lectures for diurnal motion, what I'm going to draw are some dome diagrams. The first thing that we'll do is we'll take a look at the seasons as seen from the North Pole. So what we'll do is position an observer here like so at the North Pole. And then in order to construct what the sky looks like from the North Pole, we have to do the following. You have to remember that the celestial sphere is essentially of infinite radius. So then therefore, for that reason, the Earth can be thought of here as a point on the diagram. And then from that point, this person's horizons would then stretch out like so to the celestial equator. And then right here is the dome that the person sees as seen from the North Pole. I then draw that in the following way. Okay, so here's the horizon circle, like so. Here's my observer. And then the sky looks like a hemispherical dome overhead. Remember, once again, that the point straight overhead is the zenith. If you're standing at the North Pole of the Earth, the zenith also coincides with the North Celestial Pole. Okay, and then we have the celestial equator. The celestial equator coincides with the horizon. And then if you also recall from my lecture on diurnal motion, if you stand at the North Pole, all directions are south. Okay, and then let's begin at June 21st, and on the diagram above, notice that the sun is rather low in the sky to the right-hand side, like so. So here's the sun on June 21st. Even on June 21st, as seen from the North Pole, notice how low in the sky the sun still is. This then means that the weather is cold in the polar regions. The reason for that is because when the sun is low in the sky, the amount of radiation that you receive from the sun per square inch is a small number. That number increases, however, the higher that the sun gets in the sky. As you'll see, this explains why the weather is always warm, say, near the equator. But if you're near the pole, the sun is always low in the sky, even on June 21st, as seen from the North Pole. Therefore, the weather is cold. Okay, now, on that day, the sun would then trace out a diurnal circle like so, that is roughly parallel to the celestial equator. Neither rising nor setting, you get 24 hours of daylight. However, at noon on June 22nd, the sun is here. Noon on June 23rd, the sun is here, and so on and so on and so on. The sun eventually crosses the celestial equator on the autumnal equinox, going from the north to the south. That's the day that the sun sets, as seen from the North Pole. And then from the autumnal equinox, September 23rd roughly, down to December 21st, that's on the diagram above, and then back up to the vernal equinox like so, March 21st, the sun is entirely below the horizon. So then therefore you get 6 months of darkness. And then the sun rises on the vernal equinox, March 21st, reaching its northernmost extent once again on June 21st, completing an entire year. So you get 6 months of daylight and 6 months of darkness at the North Pole for this reason. The situation is reversed in the southern hemisphere. If you stand at the South Pole, the sun rises on September 23rd and then eventually sets on March 21st. Once again, the seasons are backwards as seen from the southern hemisphere. Okay, next what I'm going to do is I'm going to take the observer on the diagram above and then move that observer to the equator. Like so. Okay, and then once again we have to picture the Earth here as being a point at the center of the diagram like so, and then the observer here standing at the equator, that person's horizons would then go like this and intersect the two celestial poles. So then right here like so is the dome of the sky that the person sees when standing at the equator. Okay, so once again, here's the horizon circle. Here's my observer. Here's the sky overhead. Here's the zenith. Okay, and then as I indicated on the diagram above, the North Celestial Pole is way over here to the observer's left-hand side on the horizon. The South Celestial Pole is here. Therefore, this right here is the meridian. This is due north. This is due south. And then notice that, once again, the celestial equator passes through the zenith as seen from an observer who is standing at the Earth's equator. So let's say it right here. In red is the celestial equator. Where the celestial equator intersects the horizon here is due east. Where it intersects over here is due west. And then let's just take a look at noon on the three different types of day that are important here. That is the two solstices and the equinoxes. So right over here, we'll say, is the sun at noon and June 21st. And then if you compare the diagram above to here at below, notice that the sun is actually on the zenith at noon on the two equinoxes when you stand at the equator. Then on December 21st, it's then a little bit to the south like so. But regardless of the time of the year, like so, when you stand at the equator, notice that the sun is always really high in the sky, hence the warm weather that you always have when you're near the equator. And then just on one of those days, let's say one of the equinoxes, notice what happens as the Earth rotates. On the equinoxes, the sun will rise due east, hit the zenith here at noon, and then set over here due west. Those are actually the only 2 days of the year that the sun rises due east and sets due west. That is on the equinoxes, and it doesn't matter where you are on the Earth in order to see that. If you're talking about, say, the December solstice, however, notice that on that day, the sun rises like so in the southeast, hits the meridian, and then sets over here in the southwest as the Earth rotates on that day. Okay, what does the sky look like from here in Los Angeles? Well, for Los Angeles, we are roughly in a latitude of about 33 degrees north latitude or so. So I'm just going to kind of estimate that here on this diagram in the following way, like so. And then right here, I'll go ahead and draw it on this diagram. Right here is that person's horizons when standing at Los Angeles. So in order to draw that horizon here on this diagram, I would draw this line tangent to the surface of the Earth, passing through the person's feet at that location. And then right here is the dome of the sky that the person would see when standing in LA. I did, however, draw this diagram carefully. Notice that if you stand right here in Los Angeles, this right here is the zenith. Even on June 21st at noon, for example, notice that the sun is still going to be south of the zenith as seen from Los Angeles. We are too far north in order to be able to ever see the sun at the zenith or north of the zenith. From here in Los Angeles, you're always going to see it south of the zenith at noon, regardless of the time of year. Okay, now here on the board below, let me go ahead and draw that situation. Okay, once again, here's the horizon circle. Here's the sky overhead. Here's the zenith. Okay, and then the person looks to the lower left-hand side like so and sees the North Celestial Pole. So here's the meridian. This right here is due north. Here is due south. The person standing in Los Angeles is never going to be able to see the South Celestial Pole. It's always below the horizon. And then here on an angle to the right-hand side like so, in red, is the celestial equator. Okay, and then right here is due east, right here is due west. Now let's take a look at the June solstice. June 21st at noon, the sun is here. And then on that day, as the Earth rotates, the sun traces out its diurnal circle parallel to the celestial equator. I'll go ahead and draw this using black. The sun rises in the northeast, hits the meridian, and then sets like so here in the northwest. Notice that most of the sun's diurnal circle is above the horizon on this day. Only a small portion of the diurnal circle like so is below the horizon on that day. So this then explains why you have longer daylight hours near the June solstice as opposed to the winter time, which I'll draw in just a few moments. I'm also going to pause here briefly to explain to you what is meant by AM and PM. Okay, first of all, AM. AM stands for antemeridian. What that means is that the sun is east of the meridian. So starting at 12 a.m. at midnight like so, here on June 21st, for example, the sun is here. And then from 12 a.m. to noon, the sun is east of the meridian. However, from noon to midnight, then the sun is west of the meridian. This then refers to PM, which stands for post-meridian. So AM means antemeridian. That means the sun is east of the meridian. PM stands for post-meridian. The sun is west of the meridian. Okay, now here's what happens in LA on, say, the other solstice. So using the diagram above, at noon, notice that the sun is really low in the sky, like so on December 21st, way to the observer's right-hand side. That's over here. So if the sun is low in the sky, this then means that it's cold in the winter. Okay, and then on that day as the Earth rotates, the sun rises in the southeast, hits the meridian, and then sets here in the southwest. Notice that most of the diurnal circle here for the sun on that day, here's the rest of it, like so. Notice that most of the diurnal circle for the sun on that day is below the horizon. This then means that you have longer nighttime hours and shorter daylight hours when you're near the December solstice. Okay, now, as I said a few minutes ago, we are too far to the north to ever see the sun, for example, at the zenith on June 21st. In order for you to see the sun at the zenith on June 21st, you would have to be standing at a latitude of about 23.5 degrees north latitude. You're standing on the Tropic of Cancer when you do. The corresponding tropic in the southern hemisphere is called the Tropic of Capricorn. If you stand at 23.5 degrees south latitude on December 21st, you will see the sun at noon. Let me go ahead and draw that situation. I have not, as of yet, drawn a southern hemisphere diagram on the board. Incidentally, by the way, recall my lecture on the spherical Earth with respect to the town of Syene that Eratosthenes used in his calculation of the size of the Earth. Remember what I said about Syene during that lecture? At noon on June 21st, if you stand in Syene, the sun is straight overhead. On what line of latitude, therefore, does Syene reside? Syene is actually right on the Tropic of Cancer. And now, as I said, let me go ahead and draw the Tropic of Capricorn for us. So you're standing at the Tropic of Capricorn in the southern hemisphere if on December 21st at noon the sun is straight overhead. So therefore I have to take my observer here on this celestial sphere diagram and position the observer in the following way. Okay, so right here is the sun at noon on December 21st, and then boom, I would have to place my observer about right here on the diagram. And then the dome that the person would see, I'll draw the horizon like so, tangent to the surface of the Earth, passing through the person's feet here at this location. Right here is the dome then of the sky that the person sees. So you kind of have to tip it on its side a little bit in order to be able to see it when I draw it here on the lower board. Okay, so once again, here's the horizon circle, here's the observer, here's the zenith. Okay, now in this case, the person looks to the lower right-hand side and sees the south celestial pole, like so. So here's due south, here's due north, here's the meridian once again. Notice that the north celestial pole, however, is below the horizon. When you stand here at the Tropic of Capricorn, you're never going to be able to see it. Okay, and then the person kind of looks to the upper left-hand side to see the celestial equator. That's like so. And then right here is due east. Right here is due west. And then we have, for example, December 21st. That's the important day when we're talking about the Tropic of Capricorn. At noon, the sun is at the zenith, like so. And then as the Earth rotates on that day, the sun traces out its diurnal circle roughly parallel to the celestial equator. That then looks like this. Rises here in the southeast, hits the zenith, and then sets over here in the southwest. Notice that this diagram is essentially backwards of the diagram that I drew earlier for the northern hemisphere situation of Los Angeles. Here in Los Angeles, you just always take it for granted that regardless of the time of the year, basically the following happens. If you're standing here in this classroom in this direction, you're looking to the south. And over on your left is east, over on your right is west. And then regardless of the time of the year, the sun basically rises somewhere in the east, passes to your south, and then sits over here to the west. Yes, it's lower in the sky on December 21st, for example, as opposed to, say, June 21st. But here in Los Angeles, you more or less take it for granted that the sky roughly always looks the same. It's backwards in the southern hemisphere, however. In the southern hemisphere, now imagine facing to the north, like so. And then over here on your right is east, here on your left is west. And then from the southern hemisphere, you see the sun rise from the east, pass to the south of you, to the north of you, like so, and then set over there on your left-hand side to the west. The sky is backwards in the southern hemisphere, and if you've ever been to the southern hemisphere, it's very easy to get confused about which direction is which, north, south, east, and west, for this reason. Okay, and then lastly, the last important lines of latitude to draw are both the Arctic and Antarctic circles. Okay, I explained the meaning of the circles in detail in part 1 of the lecture. However, here I now want to draw what the sky looks like from one of those locations. Let me just go ahead and do so from the Arctic Circle. Okay, now, to help me draw the Arctic Circle here, I'm going to add a couple of things to this diagram. Okay, specifically, I'm going to go ahead and draw right here the diurnal circle of the sun on June 21st. Right here is noon, and then right over here is midnight. Okay, and then you're standing at the Arctic Circle. The Arctic Circle's latitude, by the way, is the complement of 23.5 degrees. It's about 66.5 degrees, 90 minus 23.5. You're standing at the Arctic Circle if your horizon does the following. Like so. It intersects the sun right here to the north at midnight on June 21st. It also, however, intersects the sun right here at noon on December 21st. You're standing at the Arctic Circle, and then right here is the dome of the sky that you would see. So let me go ahead and draw in an observer here for reference, like so. Okay, so right here is the horizon disk. Here's the observer, or horizon circle. Right here is the sky overhead. Let me neaten that up a little bit, like so. Here's the zenith. Okay, and then the person looks to the upper left to see the North Celestial Pole in the sky. Okay, notice that it's rather high in the sky when you're at the Arctic Circle. And then low to the right-hand side here in red is the celestial equator. Like so. So here is the celestial equator. Right here is due east. Here's due west. Here's due south. Here's due north. Okay, and then we have the two solstices. Those are the important days when talking about the Arctic Circle. First of all, June 21st. Okay, I'll go ahead and use black for this. At noon on June 21st, the person looks to the upper left-hand side, sees the sun on the meridian. Like so. But then on that day, as the Earth rotates, the sun traces out its diurnal circle. It looks like this. Like so. It's here at noon on June 21st. And then right here, it intersects the northern horizon at midnight. The Arctic Circle is basically as far south of the North Pole that you can be on June 21st and still see the sun for 24 hours. At midnight, the sun is right here on the northern horizon. If you go a little bit south of the Arctic Circle on this day, this then means that close to midnight, the sun would be below the horizon. The other solstice has meaning as well when talking about the Arctic Circle. Take a look at the position of the sun in the sky at noon on December 21st. Notice that it intersects the southern horizon right here. And then on that day, as the Earth rotates, the sun traces out its diurnal circle like so. It's below the horizon for the remainder of the day. The situation is reversed in the southern hemisphere for the Antarctic Circle. Here at the conclusion of this lecture, I now invite you to also do the following. take a look at the screencast that I've posted for you called the Motions of the Sun Simulator Screencast. The Motions of the Sun Simulator Screencast details an online aid for you in ultimately picturing and drawing these dome diagrams. Okay, this concludes my lecture here on the seasons.